Hello friends, let us solve an important problem on sampling, reconstruction and aliasing. Before we look at the problem, let us recall that if we have a low pass signal with spectrum MF with maximum frequency W, then if we ideally sample such a signal, then the sampled signal has the spectrum with multiple copies of the original spectrum, each copy appearing at an integer multiple of the sampling frequency. So we have copies of the original spectrum at 0, fs, 2fs, -fs, -2fs, and so on. Moreover, the extent of frequencies occupied by a particular copy is of the form kfs minus w to kfs plus w. As you can see here, when k is 0, the range is from minus w to w. When k is 1, the range is from fs minus w to fs plus w. When k is 2, so it is 2fs minus w to 2fs plus w. Similarly, on the negative side, when k is minus 1, we have minus fs minus w minus fs plus w, and so on. This is an important result we must keep in mind. Now, if the sampling frequency fs is greater than 2w, that is fs minus w and w do not overlap, these two copies do not overlap, then it is possible to exactly recover the original spectrum and therefore the original message signal. So here fs is greater than 2w. However, when fs is less than 2w, in that case the successive copies of the spectrum will overlap, and because of this overlap, even if we use an ideal low pass filter with cutoff frequency exactly w, still what we recover is the distorted version of the original signal. This is demonstrated in this problem. The problem statement is as follows. A 1 kHz signal is ideally sampled at 1500 samples per second, and the sampled signal is passed through an ideal low pass filter with cutoff frequency 1200 Hz. What is the frequency, or what are the frequencies present in the output of the low pass filter? Now note that here the given signal is a 1 kHz signal, a single frequency, that is, it's a sinusoidal signal. The Nyquist rate for this signal should be 2 times 1 kHz, that is 2 kHz or 2000 samples per second, but here it is being sampled at 1500 samples per second, and therefore we will see that when we reconstruct the signal after sampling using a low pass filter, what we get back is not the original signal but a distorted version. So let's proceed. Here w, the only signal frequency present, is 1 kHz or 1000 Hz. The sampling frequency fs is 1500 samples per second. Now we know that because of sampling, the multiple copies which are generated, they are located at frequencies given by kfs plus minus w, right? So let us examine these frequencies for various values of k. So when k is equal to 0, we get frequencies at minus w and plus w, that is minus 1000 Hz and plus 1000 hertz. When k is equal to 1, so fs minus w, that is 1500 minus 1000, that is 500 hertz, and fs plus w, that is 1500 plus 1000, that is 2500 hertz. When k is equal to 2, similarly 2fs, that is 3000 minus 1000, let us write it, k equal to 2, 2fs, that is 3000 minus w minus 1000, that is 2000 hertz, and with the plus sign it will be 4000. Similarly for the negative values of k, when k is equal to minus 1, kfs minus w, so minus fs minus w, fs is 1500, so minus 1500 minus 1000, that is minus 1500 minus 1000, that is minus 2500. With the plus sign, minus 1500 plus 1000, that is minus 500 hertz. When k is equal to minus 2, similarly we will get minus 2fs minus w, that is minus 3000 minus 1000, that is minus 4000. With a plus sign we will get minus 2000 and so on. So minus 4000 hertz, minus 2000 hertz, and so on. So it will continue this way. Let us try to show them. The original spectrum of the signal contained only one frequency at 1000 hertz. So when we show the negative frequencies also, so we'll have two impulses at 1000 hertz and minus 1000 hertz. It is for the original spectrum MF. When we look at the spectrum of the sampled signal, the frequencies are present at 500 hertz, 1000 hertz, 2000 hertz, 2500 hertz, 4000 hertz, and the corresponding negative values. Let us show them. So we have the frequency components at 500 hertz, 1000 hertz, 1000 hertz, 2000 hertz or 2 kilohertz, 2500 hertz, 4000 hertz, and so on, and all the negative corresponding frequencies as well. So minus 500, minus 1000, minus 2000, and so on. We did not show all of them, only the important ones I have shown. Then this is minus 2000. Now, according to the question, if such a sampled signal is passed through an ideal low pass filter with cutoff frequency 1200 hertz, what will be the frequencies present in the output of the filter? So the cutoff frequency of the low pass filter is 1200 hertz. So 1200 will be somewhere here. So this is the frequency response of the low pass filter. This frequency is 1200 hertz. This is 1200 hertz. Similarly, this is minus 1200 hertz. So clearly it will reject all other frequencies outside this frequency range, and what is contained inside will be allowed to pass through it. And what frequency components are present here? 500 and 1000. So at the output of the low pass filter, we'll observe two frequencies, one at original 1000 hertz or 1 kilohertz and another extraneous frequency at 500 hertz. So clearly, because here the sampling was done at a rate less than the Nyquist rate, we observe some high frequency component of the sampled signal appearing as a low frequency, and this is what is known as aliasing. Thus, the frequencies present in the output of the low pass filter are 500 hertz and 1000 hertz. This problem could be removed by sampling the signal at a rate greater than the Nyquist rate. That's all. Thank you.